Have you made homemade ice cream before? So you mix the milk and the sugar and stuff, and then you need ice to freeze it, right? Can you just use regular ice? No, you can't. You have to put salt in the ice. That might seem strange. Like, what do I have to do that for? But it's the recipe, so you did it, and it worked. Great. If you try to do it without the salt, the ice cream will not freeze. What the salt does is it lowers the temperature at which the solution freezes down to about minus 10 degrees Celsius instead of 0 degrees Celsius. So adding salt makes the ice colder. It's very bizarre. That's depressing the freezing point. We call it freezing point depression. This is a colligative property. And as a group, colligative properties depend on the number of particles that are in the solution, not on what the particles are, just how many particles there are. So this is where it's behaving a little more like a gas, where it was just the moles of gas particles. It didn't matter which ones they were. Here we're looking at the number of particles dissolved in solution. If we have an electrolyte that's dissolved versus a non-electrolyte, the behavior is going to be a little bit different, because when an electrolyte dissolves, it forms more than one particle, right? You dissolve sodium chloride, you get sodium ions and chloride ions, you get 2 particles from one. Whereas a non-electrolyte like sugar, you dissolve that, one sugar molecule gives you 1 dissolved particle. And so you're going to get different numbers of particles. Vapor pressure lowering is also a colligative property, and we can look at this in terms of dynamic equilibrium. So here we have a closed container with water, let's say, and the water is evaporating, and then it gets into the gas state, and it bounces around. It can't get out. Ignore that little hole there. And it's going to recondense. And so we have evaporating and condensation, and it's in dynamic equilibrium. When we put a solute into the water, the solute gets in the way of things evaporating. Because this is where we talked about Red Rover. In order for the water to evaporate, it has to come to the surface and have enough energy to break loose. So when we have a solute in here, we've got things standing in the way. So maybe these are trees or big bully kids that won't leave the field so we can play Red Rover. They're in the way. And so not as many water molecules can evaporate because these solute particles are taking up some of the surface. That make sense? So because the rate of evaporation is less, then the rate of condensation will keep going until they become equal, and now we're going to have smaller rates in both directions. The result is we have fewer gas particles above this liquid. Fewer gas particles in that same volume is a lower pressure. So by adding a solute to this water, we lower the vapor pressure. Any questions? A more fundamental explanation is involving nature's tendency towards mixing, the increase in entropy. And this is really, really trippy. So here we have 2 beakers containing liquid. This is pure solvent, we'll say that's pure water, and this one's got salty water. And you put these in a closed environment. So here they are separate from each other, but they're under this cake plate, right? So together they're enclosed. And then you wait, and this could take a while. You come back later, and the level of liquid in the salty water beaker has gone up, and the level of water in the pure water beaker has gone down. The water has moved through the air from one beaker to another. Why? Entropy. It's trying to spread its energy out, trying to make the concentrations of both of these solutions equal. The water can evaporate, the solute particles can't. They're stuck over here. They can't evaporate. So as the water evaporates, it's going to come over here and dilute this solution. That's the spreading of energy. Yeah.
Well, if you leave it under there long enough, will the beaker containing just the water eventually be empty?
I think it would.
Yeah.
Yeah. I think it would eventually be empty. Well, the salt would change the freezing point of the water, but it's not going to just change the temperature of the solution.
Well, I meant by we get the pure water that's evaporating.
Yeah, the evaporation rate would be different. So like if you're looking at the cooling effect or the rate of evaporation, that's going to be different. Yeah. And so we can also explain this in terms of rate of evaporation and condensation. The rate of evaporation from this beaker is larger than from this beaker because this beaker has part of the surface blocked by the solute particles. The rate of condensation into both beakers is the same. So we have more water evaporating from this beaker than this one, and they're condensing the same, and so there's going to be a gradual movement of water from this beaker to the other one. So we can look at it in terms of rates of evaporation and condensation, looking at the particles getting in the way, but really what's going on is the entropy. Any questions? Isn't that weird? It's weird. So we can quantify how much the vapor pressure is lowered, of course, right? Got to quantify everything. And this is Raoult's law, and this is the Raoult who is quoted in the first slide of this chapter. So Raoult's law says that the pressure of the solution is equal to the mole fraction of the solvent times the pressure, the vapor pressure of the pure solvent. So the mole fraction of the solvent, if you had pure solvent, what would its mole fraction be? 1, right? Because it's moles of solvent divided by moles of solution. Well, if you don't have any solute, then it's moles of solvent divided by moles of solvent is pure, it's 1. Then the pressure of the solution is equal to the pressure of the pure solvent. If it's only half solvent, then that's going to affect the pressure. The pressure is going to be half as much as if you had a pure solvent. So the vapor pressure is directly proportional to the amount of solvent in the solution. So this is a useful equation. That is Raoult's law, but a more useful version of it is the vapor pressure lowering. And there's a very subtle difference here. This is the mole fraction of solvent. This is the mole fraction of the solute. So that's going to give us the change in the vapor pressure. The original pure solvent vapor pressure times the mole fraction of the solute is going to give us the change. So calculate the vapor pressure at 25 degrees Celsius of a solution containing 55.3 grams of ethylene glycol and 285.2 grams of water. The vapor pressure of pure water at 25 degrees C is 23.8 torr. So they're asking us not for the change in vapor pressure, but for the actual vapor pressure. So we want to use Raoult's law, which says that the vapor pressure of this solution, the vapor pressure is equal to the mole fraction of the solvent, here the solvent is water, times the vapor pressure of pure water. So they gave us the vapor pressure of pure water. I was going to write 23.8 equals 23.8. That's brilliant. That's the vapor pressure of pure water. So we got that. We need the mole fraction of water in this solution. So the mole fraction of water is going to equal the moles of water divided by the total number of moles, which is moles of water plus moles of, I'm going to call it EG, ethylene glycol. Now, they didn't give us moles of either one, but they gave us masses, and we can convert those. So I've got 55.3 grams of ethylene glycol. I can convert that to moles using the molar mass. So that looks like 2 carbons and 2 oxygens and 6 hydrogens. 62.068. So 55.3 divided by 62.068. 0.89095 moles of ethylene glycol and 285.2 grams of water, and I'm going to use its molar mass to convert to moles of water. So the grams cancel out. 285.2 divided by 18.02. 15.8268 moles of water. So I can plug those into my mole fraction equation. I've got my moles of water on top. And moles of water plus moles of ethylene glycol on the bottom. I'm going to do that carefully on my calculator. And I'm getting 0.94670. Actually, that should have 4 sig figs. 706. And again, the moles cancel out, and so mole fraction has no units. Mole fraction cannot be more than 1. So if I get, if I got 9.4, I should check my math. But it's less than 1, so it's probably good. So I can plug that in over here for the mole fraction, 0.946706, times the vapor pressure of pure water, 23.8 torr. That's an excellent question. Can it stay in torr? Well, if it's open-ended like this, sure. If it's multiple choice, depends on what unit is given for the answer choices. So 22.531 torr. So 22.5 torr should be the vapor pressure of this solution. So adding some ethylene glycol reduced the vapor pressure of the water. Any questions? .5 torr. So here the answer in the back of the book was in torr. What if your solute is volatile. So volatile means evaporates easily. Up to now, we've talked about things like sodium chloride. Sodium chloride doesn't evaporate, right? It's just going to stay in the beaker. But what if I've got two liquids, say, and one of them, or both of them are going to evaporate? Well, if we have an ideal solution, like an ideal gas, it's going to follow the rules and be nice and predictable. So an ideal solution is going to follow Raoult's law at all concentrations for both the solvent and the solute. We can calculate either one. So above an ideal solution, the total pressure is going to be the partial pressure from each component of the mixture. So the solvent is going to have a vapor pressure, and here the solute is also going to have a vapor pressure. The total pressure is equal to the sum. If it's a non-ideal solution, then it doesn't follow Raoult's law because of interactions between the solute and the solvent. If the solute and the solvent really, really like each other, if they're very attracted to each other, that's going to reduce the rate of evaporation for both. It's going to reduce the vapor pressures. If they don't like each other, if they kind of are like trying to get away from each other, it's like we're in solution here, but I'm not really crazy about you. Then that's going to increase the rate of evaporation, and it'll cause the pressures to be higher than predicted by Raoult's law. So this is a graph showing the vapor pressure of each component as a function of the mole fraction of A. And we see that when the mole fraction of A is 0, then its vapor pressure is 0. And the mole fraction of B here would be 1, so all the pressure is from B. And as we mix these, so we have more A and less B, the vapor pressure of B goes down, that's the blue one here. The vapor pressure of B goes down, the vapor pressure of A goes up. Over here, the vapor pressure of B is 0 because there isn't any B. It's all A, and all we have here is A. The combined vapor pressure of the solution is the sum of those two at all places. When we have strong interactions between the solute and the solvent, then we see these lines bow down from what is expected. The expected is the dashed line. And here, because the solute and the solvent, A and B, are attracted to each other, they're not going to leave as easily, and so the pressure observed is less. When they don't like each other, they're going to leave more easily than in an ideal solution, and so the vapor pressure is going to be higher. Now, deviations from ideal behavior may or may not matter depending on what your application is, but it's important to understand that these can exist. Because if you have something like this where the vapor pressure is higher than you were expecting, you could have your container blow up, possibly, right? It's going to mess things up. Okay, this is a fun one. A solution of benzene and toluene is 25% benzene by mass, and at 25 degrees Celsius, the vapor pressure of pure benzene and pure toluene are 94.2 torr and 28.4 torr, respectively. Assuming ideal behavior, calculate the following: the vapor pressure of each of the solution components in the mixture. Okay, we can do this. It's just tedious. So they're wanting the vapor pressure of each component. We have two components. We have the toluene and the benzene. I'm going to call them T and B. And so we've got the pure vapor pressure of benzene is 94.2 torr, and the pure vapor pressure for toluene is 28.4 torr. And we're told that this is 25% benzene by mass. So 25.0% benzene. That means I have 25.0 grams of benzene per 100 grams of solution. It's asking me to find the vapor pressure of benzene and vapor pressure of toluene in the mixture. And for that, I need Raoult's law. So the vapor pressure for the benzene is going to equal the mole fraction of benzene times the vapor pressure of pure benzene. Well, I have the vapor pressure of pure benzene, so that's nice, but I need the mole fraction. And what I've been given is a mass percent. So to convert this into a mole fraction, I need to know how many moles of benzene do I have and how many moles of toluene. So this one is going to require a little bit of problem solving. Converting the 25 grams of benzene to moles, that's fine, right? But 100 grams of solution, how do I convert that to moles? It's two different things. It's got two different molar masses. I need the mass of toluene. So let's think about this. I have 100 grams of solution and 25 grams is benzene. What's the rest? The toluene. So that means I have 75 grams of toluene, because 75 and 25 adds up to 100. So can I convert 75 grams of toluene into moles? Yeah, I can do that. So 75 grams of toluene, and the molar mass of toluene. Hey Siri, what's the molar mass of toluene?
The answer I found is 92.064 atomic mass units.
So 92.06 grams per mole. We could calculate that, but I don't feel like it right now. So 0.81468 moles of toluene. It's important not to round stuff off too much. We don't want to round this to 0.8, okay, because that's going to give us a wrong answer, and it's not going to really save us that much time. If we're going to do the problem, we might as well carry at least one extra digit and get the correct answer. And so we also need the moles of benzene. Hey Siri, what's the molar mass of benzene?
The answer I found is 78.047 atomic mass units.
So 78.047, 25 divided by 78.047. So that's my moles of benzene. So I need the mole fraction of benzene. The moles of benzene divided by the moles of benzene plus the moles of toluene. I'm getting 0.282. the mole fraction of benzene. Anybody else get that? So then over here, the pressure of benzene is going to equal the mole fraction of benzene times the vapor pressure of pure benzene. Call that 26.6 torr. That's for the benzene. And when we need the partial pressure of the toluene. So pressure of the toluene is going to equal the mole fraction of toluene times the vapor pressure of pure toluene. I can use a kind of a shortcut here. If this is the mole fraction of benzene, the mole fraction of toluene is 1 minus this. Because there's two components, they have to add up to 1. So 1 minus 0.28221 is 0.71779 times the pure, or the vapor pressure of pure benzene, toluene, .385, 20.4. That's the benzene, and this is the toluene. Any questions? I got the 0.7 by taking 1 minus 0.28221. Because just like percentages have to add up to 100, fractions have to add to 1. I could calculate it by doing this thing again, but with the 0.81468 in the numerator, I get the same number, but it's just kind of tedious. Any other questions? 26.6 and 20.4. Yes. Now it's asking us to calculate the total pressure above the solution. This is part B. This one's actually much easier than the first one. What's the total pressure? It's the sum of the partial pressures, right? So the total pressure is going to equal the pressure from the benzene plus the pressure from the toluene, which, if I remember correctly, was 26. No, it was 20.4. No, it was 26. 26.6 plus 20.4. Gotta do the math right. 20.4 plus 26.6, 47. And sometimes, especially if you're like taking an exam and your brain is like a little stressed out, you're like, wait a minute, that's too easy. It couldn't be that simple. Sometimes it is. 47. Now this is the bear. Calculate the composition of the vapor in mass percent. Well, what does that mean? So if I'm looking at percent benzene, I'm looking at the grams of benzene divided by the grams of benzene plus the grams of toluene times 100 in the vapor. What's the relationship between the moles or the mass of a gas and its vapor pressure? How about PV equals nRT? I know the pressure of the partial pressure of the benzene. I've got the temperature, it's 25 degrees Celsius. I've got R. I want N, but I don't know what the volume is. Well, I'm going to have to do this for the toluene also. I could just choose something convenient, like a liter. So what I'm going to do is I'm going to choose 1 liter of gas mixture. So then the moles of benzene is equal to the partial pressure of benzene times the volume, which is 1 liter, divided by RT. So the partial pressure of the benzene was the 26.6 torr, right? But can I use torr in the ideal gas law? No, I can't. 26.6 torr divided by 760, that's going to give me atmospheres, times 1 liter divided by 0.08206 liter atmospheres per mole Kelvin, temperature in Kelvin, 298 Kelvin. Yes. I got the 26.6 from the part A. So that's the partial pressure of benzene in the gas above. Yeah. Yep. So this 26.6 is the partial pressure from part A that we calculated. Here I'm just converting it to atmospheres in the problem because I don't have much space on this slide. So this is giving me moles of benzene, and so I can convert that to mass. Let's see, I believe it was 90 benzene, toluene. The benzene was 78.047. So 0.001431 times 78.047. This is my mass of benzene. So percent benzene will be the mass of benzene divided by the total mass so I need the mass of toluene also. So same type of calculation, moles of toluene is going to equal the partial pressure of toluene times my chosen 1 liter divided by RT. And from that first slide, it was 20.4 torr. So dividing by 760 gives me the atmospheres times 1 liter divided by 0.08206 liter atmospheres per mole Kelvin times 298 Kelvin. I'm sorry, 20.4 divided by 760 divided by 0.08206 divided by 298. 0.00097 moles. And I need the molar mass of toluene again, 92.06. So I've got my mass, my moles times 92.06. And this gives me 0.10105 grams. And so I can put that in up here. .5% benzene. There's 2 things in this mixture, so the rest of the 100% must be the toluene. So 100 minus 52.5, 47.5% toluene. And then here's an interesting question. Why is the composition of the vapor different from the composition of the solution? The solution was 25% benzene by mass. The vapor is 52%. Why isn't it the same?
Because toluene has a double bond with the carbon, so it requires more energy to break, so less of it evaporates.
Yes, but overthinking it. We actually don't need to know what the structures are at all. But it does have to do with one evaporating faster than the other. What are their partial pressures? Their pure vapor pressures, I mean. So pure benzene has a vapor pressure of 94, and pure toluene has a pressure of 28 torr. So this higher vapor pressure, and it's like 3 times higher, right, says that benzene evaporates more rapidly than toluene does. So although the solution is 25% benzene, that's more volatile than the toluene, so it's going to contribute more to the composition of the vapor than the toluene will.